Hey guys, this is Mr. Bennett. This is Unit 4 on electrons, and you're watching video 4-2 Part 1. The reason why there's a Part 1 and a Part 2 is that I'd like you to take a break in between. I feel like to watch a 20-minute video and really focus and really get a lot out of it is really tough. So take a break in between, watch the first part, get up, stretch, do what you gotta do, then come back and watch the second part, then do your whisk. Okay, so in 4-1 we talked about energy levels and we talked about the sub-levels that they contain. So in this video we're going to talk about how to diagram or how to illustrate or draw what those orbitals and their sub-levels look like. Okay, so we talked about energy levels. The first energy level has the S sub-level. The second energy level has two sub-levels. Okay, remember the energy level itself tells you how many sub-levels it has. So energy level 2 has two sub-levels, the S and the P. Third energy level has three sub-levels, the S, the P, and the D. Okay, and so the fourth energy level would have 4, S, P, D, F. Okay, your diagram looks like this. Same idea, only instead of lines to represent, again the lines represent orbitals. In my diagram over here, I have a box. It represents the same thing, orbitals. And orbitals can hold, if you remember from last video, 2 electrons each. Okay. Now, remember, is the further away we get from the nucleus, the more energy those orbitals represent. Okay. All right. So in this video, the main idea that we are covering is how to show electrons and their arrangement around the nucleus. So in other words, where are these electrons? Remember, quantum mechanics say that we can determine where the electrons are 90% of the time. So that 90% of the time, how are they arranged in the orbitals? Which orbitals are they occupying? Where could we find them? There's two methods we can use. There's orbital notation and there's electron configuration. The main difference is with orbital notation, we're going to use arrows to represent the electrons. These arrows will be up arrows or down arrows. And then in electron configuration, we'll use numbers like 1, 2, etc. to represent the electrons themselves. Okay, so we're just counting them, 1 electron or 2 electron or 3 or 4. Okay, in both cases, no matter which method we use, there are 3 rules that we have to follow when we are explaining where the electrons are found. Okay, so we're going to start off explaining these 3 rules. Rule number 1 is called the Aufbau Principle. And I think of this like building a house. In other words, electrons have to occupy the orbitals of the lowest energy level first. So in terms of a house, it means you have to start with the foundation and then you build your way up. Okay, you got to build it from the bottom up. The electrons get filled from the bottom up, meaning the lowest energy level up. Now, there's a catch to this. If you remember last video, as we get further away from the nucleus, the energy levels start to get closer and closer to each other. And so what happens is we eventually get a little bit of overlap. So it creates an exception in the order that we would normally memorize. You need to know this section right here. Okay, this diagram right here is known as the rule of diagonals. And what it says is if we start closest to the nucleus, we have the first energy level, which has an S sublevel. The second energy level has an S and a P. The third energy level has an S, a P, and a D, and the fourth energy level has a 4S, 4P, 4D, 4F, etc. Okay. Now we fill these using the diagonal lines. So we'd fill the 1S, then we fill the 2S, then we fill the 2P, and then the 3S, then the 3P, then the 4S. Notice I went from 3P to 4S, then 3D, then 4P. This is because as we're going out from the nucleus, it turns out that the 4S is slightly closer to the nucleus than the 3D. Therefore, the 4S has slightly less energy than the 3D, so we fill it first, and then we fill the 3D, and then the 4P. Its Aufbau Principle is all about energy. So you fill the lowest energy level first. The 4S has slightly less energy than the 3D, so we fill it first. Okay, so the order you need to know is right here. Okay, and the exception is in the third energy level. Right after the 3P, you fill the 4S and then the 3D. You don't need to know anything beyond 4P. You just need to know this order right here, and it occurs. You have this little weird thing in the order because the energy levels overlap. The 3 overlaps the 4. Okay. Rule number 2, the Pauli exclusion principle. The way I remember this one is that P, the P in Pauli, stands for pattern. Electrons need to fit it or they get kicked out. Okay. So kind of wordy, but it says an atomic orbital may describe at most 2 electrons, and they have to spin in opposite direction. I mentioned earlier that with orbital notation, we use arrows to represent the electrons, and they can be up or down. The up or down is a way of representing the spinning of the electron. So it can spin up or it can spin down. For example, if we have hydrogen, hydrogen has 1 electron. It has an atomic number of 1 proton, and 1 electron. If I draw the orbital as a box, okay, then I would just draw 1 arrow. And we always start with the up arrow, the up spin. So it's just got 1 electron filling that orbital. If I were to use a line, do a line to represent my orbital, and I'd have an up arrow. Helium, on the other hand, has an atomic number of 2. That means 2 electrons. So when we fill its orbital, we need an up arrow and a down arrow. They have to have opposite spins or they get kicked out. In other words, this electron would get kicked out if it were up. Okay? So in other words, we never fill our orbitals like this, up, up, or like this, down, down. Okay? That is wrong. Okay? So as I would fill this in, I'd follow Pauli exclusion when I'm filling these in. I would go up arrow, and then I'm like, okay, I need to put a second electron in here, so I go down arrow. Okay? Third rule, Hunds rule, I think of as the movie theater rule. What does that really mean? Well, we spread out in movie theaters. I don't know about you guys, but if I were to go see a movie with my friends, okay, we're guys, okay, we're friends, but we're not that friendly. So if we go in the movie theater and the orbitals are represented like seats, okay, I would sit here. Even though he's my best friend would probably sit right here. And we're assuming the movie theater has plenty of empty seats. Okay, forgot to mention that. So I sit here, my best friend sits here, my other friend sits right here. Okay, notice we've left seats in between us empty. Okay, I can put my drink here, I can drink my drink. I don't have the awkward situation in the middle of the movie where my friend accidentally grabs my drink and I'm like, bro, that's my drink. You know, leave it alone. I don't want whatever, you know, diseases you have or whatever it is, right? And so he can put his drink here and he doesn't have any like awkward situations with him. And so maybe he puts his drink over here because he's really worried someone's going to take it, okay? But the point is we spread out, okay? Same things happen with couples. Couples come in, they sit down, they leave a little gap, right? Next couple comes down, they sit leave a little gap here, okay? We spread out. We don't double up. We don't squish next to each other until we have to. Electrons follow the same idea. When electrons occupy orbitals of equal energy, 1 electron enters each orbital and you don't double up until you have to. Okay? Let me explain what I mean. First of all, this doesn't apply to the 1s or the 2s because they only have a spot for 2 electrons. So before you can move on to the 2s, you have to fill the 1s with 2 electrons. Before you can move on to the 2p, you have to fill the 2s with 2 electrons. So there's no spreading out here. You have to fill it with 2. Okay? But once you get to the 2p, notice carbon has 6 electrons, right? So it puts 2 electrons in the 1s, then it moves on and puts 2 electrons in the 2s. When it gets to the 2p, it puts 1 electron here and 1 electron here. The p sublevel has 3 orbitals. So it's going to put 1 electron in one, 1 electron in another. They're not going to double up because they don't have to. They're going to spread out just like the movie theater. Nitrogen has 3 electrons in the 2p. So they're going to spread out as well. 1, 2, and 3. Each of them is going to go to a different orbital in the p sublevel. Okay, they're not going to double up because they don't have to. Okay, and notice they have the same spin right now. We always do the up arrow first. Okay, now when we get to oxygen, oxygen has to put 4 electrons in that p sublevel. So there's 3 orbitals, right? So I go up arrow, up arrow, up arrow. Now that final 4th or 8th electron has to go in, still has to go into the p sublevel, but there's 1 electron in each orbital. So now I double up, okay, and I put a down arrow because I got to follow Pauli exclusion. Okay. Notice with fluorine, fluorine has 1 more electron, so those 3 orbitals, I go up, 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 down, down. Okay. So again, Hunds rule, you don't double up until you have to, and you still follow Pauli exclusion, meaning they have opposite spins when they do double up. Okay. So those are the 3 rules. Let's do practice real quick. I know we just did this one, but let's try it again. Oxygen has an atomic number of 8. Why do I care about the atomic number? Well, the atomic number is also the same or equals the number of protons. And because oxygen is neutral in this case, it also tells us the number of electrons. So that means that it has 8 electrons. we want the orbital notation, which is a way of describing where these electrons are found. Okay, and remember, orbital notation is all about arrows. Okay, so in other words, we need to fill this up with 8 arrows. There's 3 rules we need to follow. The first most important rule is the Aufbau rule, meaning we start with the lowest energy level 1, and we work our way up. Okay, on your handout, instead of going up like this, you have lines. So it's going to be 1s and a line to represent this box. Okay, then you have 2s with a line to represent this box. Then you have 2p with 3 lines to represent these 3 boxes. Okay, so, and you don't have these guys up here because they're actually not needed. Okay, so on your diagram, the energy is increasing as we go to the right. Okay, so just like I fill out these boxes, you're going to fill in these lines. So we have 8 electrons or 8 arrows to place. We start with the lowest energy level, so that'd be the 1. We always do an up arrow first, and then a down arrow. The 1s can only hold 2 electrons, so we put 2 arrows in here. Aufbau says we start with the 1. Poly exclusion says the arrows have to be in opposite directions, up or down. Okay, and then we don't care about the Hunds rule yet because the 1s only has 1 orbital. Now we move on. Our 3rd electron goes here, up arrow. Our 4th electron goes here, down arrow. Okay, the 2s is now filled, so we move on to the 2p. Okay, 4 electrons are placed. We need to place 4 more. So I go 1, 2, 3, and 4. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8 electrons. I followed the Hunds rule. I filled in this box, then this box, then this box, or this orbital, then this orbital, then this orbital. Put 1 in each before I came back and doubled up. And according to Poly exclusion, I had the arrow that did double up in the opposite spin, meaning pointing down. Okay, so you'll fill these in the same way. All right, so that's the end of part 1. Take a break, come back, watch part 2, finish your notes, and then do your whisk.